Hello everyone, this is Surajit and you are welcome to our channel. Yeah, in last few lectures we have talked about Coulomb's law, where we have learned how to calculate force between two charge, as well as if we have a more than two charge, we have learned how to calculate force on a particular charge using superposition principle. Later on we have also learned how to calculate electric field for a single point charge, as well as we have also learned how to calculate electric field for large number of discrete point charges. And at the end, we have talked about electric field due to continuous charge. Here we have learned how to calculate electric field for an infinitely long charge carrying wire on the axis of a circular loop and at the center of a charge carrying arc, and also on the axis of a charge carrying circular disk. So in this video, we will solve some problem based on the theory that we have already discussed in last two lectures. So let's start. So this is question number 1. So let's see what we have to solve in question number 1. It is written in question that consider 2 point charges q and lambda q located at a point x equals to a and x equals to mu times a respectively. Assuming that the sum of two charges is constant, what we have to calculate then? What is the value of lambda for which the electrostatic force is maximum? Okay, so let me draw a figure first, and let's say this is our x-axis and this point is x equals to 0. Now consider 2 point x equals to, let's say, a and x equals to mu times a. Okay, so on the x-axis we have considered 2 point x equals to a and x equals to mu times a. Then 2 point charges are placed at x equals to a and x equals to mu a, and their charge are q and lambda times q. Lambda times q. Now what has been written in question that the sum of these two charges is constant. Sum of these two charges is constant. So let me write here, given q plus lambda q is equals to constant, and let's say this constant is some q naught or q naught. Okay, so this is condition 1, and then what we have to do, so we have to calculate the force, and then exactly we have to calculate the value of lambda for which the force between these two charges is maximum when their position are fixed at x equals to a and x equals to mu a. Okay, so when two charges are at fixed position, then we have to calculate for what value of lambda this force between these two charges is maximum under this condition that the charge of summation of charge of sum of the two charge is constant. Okay, so okay, so then first write the force between these two charges. So right here the force between two charges is F is equals to what we can write, Coulomb constant, and then product of these two charges, so q into lambda q divided by square of the distance between these two charges. So what will be the distance between these two charges? In this case it will be mu times a minus a, so we can write mu minus 1 whole square into a square. Okay, so this will be the force between these two charges. Now what we have to do, So it has been asked for what value of lambda this force will be maximum. But from the given condition, we can say that this q, small q, is also a function of lambda. So let me first write the small q in terms of lambda. So q in this case will be some constant q naught divided by 1 plus lambda. 1 plus lambda. So if we put this value of small q in this equation, what we'll get? We'll get k, and then it will give you lambda into q square. So we can replace this small q in terms of lambda. So then what we'll get? We'll get a k q naught divided by mu minus 1 whole square into a square lambda divided by 1 plus lambda whole square. 1 plus lambda whole square. Now this quantity are constant in this case. This term are constant. So only this part is a function of lambda. So now what we have to do, we have to calculate for what value of lambda this force will be maximum. So for that, what we can do, we can simply take the derivative of this force in terms of with respect to lambda, and then if we make it 0, from there we'll get the value of lambda, and for that particular value of lambda, force will be maximum. So let me write here for maximum value of f del f by del lambda with 0. So what we have to do, we have to take the derivative of this f with respect to lambda. So when you take the first derivative of the f with respect to lambda, what we'll get? We'll get 1 divided by 1 plus lambda whole square minus 2 into lambda divided by 1 plus lambda whole cube, and this is equals to 0. And if you simplify this term, what we'll get? We'll get 1 plus lambda minus 2 lambda. This is equals to 0. And from there, what we'll get? We'll get lambda equals to 1. Lambda equals to 1. So that simply suggests that when two charges are at a particular distance, another way we can say when the distance between two charges are fixed, then the force between them will be maximum when their magnitudes are equal. You see, if we put lambda equals to 1, then what we'll get? We'll get q and q. So when both the charges have same magnitude for the particular distance between them, then the force between them will be maximum. Force between them will be maximum. And what will be correct answer? Correct option? Correct option is option B. So option B is correct. Option B is correct. Okay. Now take a look on second questions. So in second question, it is written that 4 equal point charges Q are placed at the corner of a square of side A. The magnitude of force on each charge is. Okay. So let me draw a square. Let's say this is a square of side A. Each side have a length A. And then 4 equal charges, and each of charges is Q, 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 Q. Okay. So 4 identical point charges are placed at the corner of this square. Okay. So now what we have to do, we have to calculate the magnitude of force on each charge. Since all charges are identical, so force on each charge, magnitude of force on each charge will be actually equal. So we can calculate force on one of them. So let's calculate the force on this charge. This one. This one. So for that, just let me write the charge in this way. Let's say this charge is Q1, this charge is Q2, this charge is Q3, and this charge is Q4. But according to questions, Q1, Q2, Q3, Q4 all are same, and that is equals to Q. So let's write it this way. Q1 equals to Q2 equals to Q3 equals to Q4 equals to Q. Okay, equals to Q. So now we want to calculate force on Q1, and in this case we have total 4 charges. So what we have to do, we have to use superposition principle of force. And if we want to use superposition principle, then what we have to do first, we have to calculate the force on this Q1 because of other charges individually. That's when we have to calculate the force on Q1 because of only Q2, because of only Q3, and because of only Q4. And then according to superposition principle, we added all these three force together, and that will give us the net force on Q1. Q1. So let me write here one by one. So write here the force on Q1 due to Q2 is F12. So we can write Coulomb constant, and then product of these two charges Q1, Q2, in this case both are Q, so it will be Q square divided by the distance, square of the distance between them. So in this case this is Q2 and this is Q1, so the distance between them actually A, so it will be a square. It will be a square. And what will be the direction of this force? So this direction of the force F12 will be along this direction. They are same type of charge, so they will repulse each other. So that therefore the force on Q1 because of Q2 will be along this direction. So this is the direction of F12, and what will be magnitude? KQ square divided by S square. Similarly, we can also write the force on Q1 due to Q3 is F13. So what will be the magnitude F13? Again, Coulomb constant, product of these two charges Q1, Q3, both are Q, so it will be Q square divided by square of the distance. So in this case, what will be the distance of these two charges? So the square has side A, so the length of the diagonal will be root 2 times of A. Root 2 times of A. So in this case, the distance between Q1 and Q3 is root 2 times A. So what we have to put here, root 2 times A, square of root 2 times A, and that will give you 2A square. 2A square. So this is the force on Q1 because of Q3. And what will be the direction of this force? Direction of this force will be along this direction, along the diagonal of this square. Okay, along this direction. So this is the direction of F13. Okay, and then the force on Q1 due to Q4 is F14 is equals to K Q square divided by distance between these two charges. So in this case Q1, the distance between Q1 and Q4 is again the sides of the length of the side of the square, so it will be A, so S square. Okay, and what will be the directions of F1 force? This will be along this direction, along this direction. This is the directions of F1 force. Now, according to superposition principle, if I want to calculate the net force on Q1 because of other three charges, so what we have to do? Then we have to take the vector sum of all these three charges, all these three forces. So now when we're going to add these three forces together, so we can add them two different way. Either we can write this F1, F2, F3 in terms of vector form, that is magnitude as well as direction. And then simply we can add them together so that X component will be added up with X component of other forces. Same way Y component will be added up with Y component. And another way we can do, what we can do, if we know the angle between each forces, like what will be the angle between F1 and F12 and F14, and what will be the angle between F12 and F13, then we can simply decompose them, and from there we can calculate what will be the net force, what will be the resultant force, and which directions it will be. So in that case, we know the angle that F1 and F4, F12 and F14 makes an angle 45 degree, and F13 makes an F1 and F12 and F14 makes an angle 90 with each other, and F13 makes an angle 45 degree with both of these two forces, F12 and F14. So in this case, we can simply decompose this force to orthogonal component. So when we will decompose this F12 to orthogonal component, one component will come along the diagonal. So one component will be along this direction, and another component will come in this direction. And same way, when we decompose this, F14. So one component again, it will come along the diagonal, this direction, and another component will go along this direction. Will go along this direction. So now take a look on the magnitude of F14 and F12. Both have same magnitude. Both have same magnitude. So because of that, this component and this component, they will cancel out each other. So resultant force will be along the diagonal, that is along the F13, direction of F13. So therefore, what will be the net force? So from figure, we can write the net force on Q1 is F net is equals to magnitude of F13 plus 2 times of cos 45 degree into one magnitude of one of these force, either F12 or F14. Because this angle is 45 degree, this will be 45 degree. So let me just put, both have same magnitude, so you can put Q square divided by S square. So then if we put the value of F13, we'll get K Q square divided by 2S square plus 2 into cos 45 is 1 by root 2, and then K Q square divided by S square. So if you take K Q square S square common, then what we'll get? We'll get root 2 plus 1 by 2. Okay. So this will be the net force, and what will be the directions of net force? The directions of net force will be along the diagonal, that is in this direction. This will be the direction of net force, and magnitude of this force will be kq square divided by s square into root 2 plus 1 by 2. Okay. So what will be the correct option? Correct option in this case will be option C. Option C will be correct option. Good. So now take a look on question number 3. What is written in question number 3? When 4 equal point charges are placed at the corner of a regular hexagon, the electric field at the center is E0. If another charge is removed such that the charge from 2 adjacent corners are missing, then the electric field at the corner will be. Okay, nice question. So let me write 2 cases here, case 1 and case 2. This is case 1 and let's say this is case 2. So both the cases we have to draw a regular hexagon. Yeah. Yeah. And then usually, each regular hexagon have 6 corners, but in this case, in first case, we have only 5 charges. So we can put 5 charges at 5 corners. So one corner will be missing. One corner there will be no charge. So this corner there is no charge. There is no charge at this corner. And if we assume that the side of this regular hexagon, each side should be equal, and side let's say A, and from the properties of regular hexagon we can say also that the distance of each corner from the center will also be A. That's mean the distance of the each charge from the center will be same and it will be A. So now what we have to do, you have to calculate electric field at the center. So what we have to do, since we have 5 charges, that is more than single charge, so we have to use superposition principle. And if we want to use superposition principle, then what we have to do, first we have to calculate electric field because of individual charges. So in this case, from figure 1, we can see that this charge and this charge, they are exactly opposite to each other, and they will create an electric field at the center of same magnitude, but the directions of electric field will be opposite to each other. Let me just join these 2 charges. So this charge will create electric field along this direction, and this charge will create electric field along this direction. So these 2 electric field will be opposite to each other, and all the charges have same magnitude and they are situated at same distance from the center. So each charge will create a same amount of electric field at the center. So in this case, these 2 electric field will cancel out each other. So the resultant electric field because of these 2 charges will be 0. Same way, if you consider these 2 charges, they also create a same amount of electric field at the center, but the directions of electric field will be opposite to each other, and because of that, they will cancel out each other. So eventually, the net electric field at the center will be only because of this charge, because at this corner there is no charge. So what will be that electric field at the center? So this electric field will be along this direction, and since we have assumed the distance of the side of this regular hexagon A and charge, let's say Q. So what will be the electric field at the center? E will be K Q square divided by S square, and in this case, in questions it is written that electric field can represent E naught. So E naught is the electric field at the center because of a single charge Q, and this will be the directions of E naught. Okay, so let me write in this way. Let's say write it as 1 q e1. Okay, so now come to the second case. In second case, what has been written in question, that if another charge is removed such that the charge from two adjacent corners are missing, then the electric field at center. So now what we have to do, we have to remove another charge from these 5 charges, so that initially there was no charge at this corner. Now we have to remove one of the charge from this 5 charge in such a way so that this corner, there will be no charge on this corner, as well as either this corner or this corner there will also be no charge, so that two adjacent corner will be missing of charge. So let me remove the charge from this corner. Then we can draw like this way. One charge will be here, another charge will be here, another charge. So now we have only 4 charges in our system. So 4 charge we can place like this. So now two adjacent corner, this corner and this corner, there is no charge. Okay. So again, we have to calculate the electric field at the center. So in this case also you can see that this charge and this charge, let me just add them together. So they will create again same amount of electric field at the center, but directions of the electric field will be opposite to each other, and because of that they will cancel out each other. So now the net electric field at center will be because of this charge as well as this charge, and we know the electric field of individual charge at the center is represented by E naught. So in this case, for first charge, for this charge we can write that electric field will belong this direction, and that we have written E1. E1 is equals to E naught. And also now since there is no charge, so this charge will also create electric field, and this electric field will belong this direction. So let me write is E2, and it is also have magnitude E naught, and directions will belong this direction. Okay. So now we have to calculate the net electric field. So we have to add this E1, E2 together. And then we have to calculate magnitude of actually the resultant electric field. So for that, in this case, again, from the properties of this regular hexagon, we can say that the angle between these two lines is actually 60 degree. So this angle between this E1, E2 will also be 60 degree. 60 degree. So now we have two equal vectors. The angle between them is 60 degrees. So what will be the resultant electric field? So the net electric field, at the center will be E net is equals to under root of E1 square. E1 is E naught, so E naught square. E2 also E naught, so E naught square. Plus 2 into E naught square into cos 60. To cos 60. Now what is the value of cos 60? Cos 60 is half. So this 2 will cancel out. Then what we'll get? We'll get root 3 into E naught. Root 3 into E naught. Okay, so this will be the net electric field for second case. So what will be the correct option then? Correct option will be option C. Option C will be the correct answer. Okay. So now take a look on question number 4. So in question number 4, it is written that a cube of side A, point charges plus Q located at each of its vertices except from the origin, where the charge is minus Q as shown in the figure. The electric field at the center is. So what has been written in question, that we have this cube whose one corner is lies at the origin of the rectangular coordinate system, and then sides are parallel to the x-axis, y-axis and z-axis. X-axis, y-axis and z-axis. Side of the cube is A. Now cube have 8 corners, so we have 7 positive charges. So 7 positive charges is placed 7 corner, and at the origin, that means at this corner, you have placed minus q charge. Minus q charge is placed at this corner. So now what has been asked, then what will be the net electric field at the center of the cube? What will be the net electric field at the center of the cube? So again, how many charges we have in our system? So you have total 8 charges, and we want to calculate electric field at the center of, because of these 8 charges. So what we have to do, we have to use superposition principle. And according to superposition principle, net electric field will be the summation of electric field of individual charges. So first we have to calculate electric field because of individual charges. But again, from the figure you can say that this charge and this charge, they are diagonally opposite to each other, and they have same amount of charge, and they will be situated at the same distance from the center. So they will create a net same amount of electric field at the center, but their directions will be opposite to each other. So because of that, the electric field of these two charges will cancel out each other. So net electric field because of these two charges will be 0. And same way, this charge and this charge, they are also situated diagonally opposite to each other. So because of that, and they are also have same kind of charge, so they will also cancel out their electric field. And also you can see that this charge and this charge, they are also sitting diagonally opposite to each other, so they will also cancel out electric field of each other. So what will be the net electric field then? Net electric field will be only because of the charge that is situated at the corner, and this charge which is situated at x equals to a. Okay, and another charge is situated 0, 0, 0. Okay, so what will be the net electric field? Net electric field will be only because of these two charges, because they are also same charge but their magnitude is opposite to each other. So because of that, their electric field will be added up, so you'll get some non-zero electric field. So you have to calculate electric field because of only these two charges. Because of the electric field of other charges will cancel out each other. So net electric field at the center will be because of only these two charges. So let me draw a cube here. Okay, this is y-axis, this is z-axis, and this is x-axis. It's exactly same figure I have drawn what is given in the question. Now we had 8 charges, but as we have already shown in the figure that because of 6 charges, they will cancel out electric field each other. So you have to calculate only electric field because of this charge, which is minus q, is situated at origin, and we have another plus q charge at x equals to a, y equals to a, and z equals to a. And for that, we have to calculate electric field at the center of this cube. And in this case, what will be the coordinate of the center of this cube? It will be a by 2, a by 2, and a by 2. So a by 2, a by 2, a by 2. So this will be the electric field. So this will be the point where we have to calculate electric field. Okay, so let me just define in this way. This charge is q1, q1 is equals to plus q, and q2 is equals to minus q. Okay, so we have to calculate electric field because of q1 and q2. So first write here the electric field at the center of the cube because of q1. So the electric field at the center of the cube due to q1 is, let's say, E1. So what will be the value of E1? 1 by 4 pi epsilon naught, that is Coulomb constant, into what we have to write here? We have to write the charge, magnitude of charge of q1, so in this case capital Q, divided by the distance of the field point from this charge. So in this case, what will be this distance? So either we can write this r vector and then we can calculate the magnitude, or from the geometry also we can write the diagonal of this cube. Length of the diagonal will be root 3 times a. So half of that will be root 3 by 2. So root 3 by 2 whole cube into this r vector. So that is position vector of this point with respect to this point. So what will be that position vector? So in this case we can write a by 2 minus a I cap, a by 2 minus a j cap, plus a by 2 minus a into k cap. Okay, so this will give you, to simplify this thing, what we'll get? We'll get a 1 by 4 pi epsilon naught q, and then 2 cube 8, so 4 into a. Now a will cancel out, so we can write 4 divided by 3 into root 3 into a square, and in bracket what we'll get minus I cap minus j cap and minus k cap. Okay, so this will be the value of E1. Same way also we can write the electric field because of Q2 exactly same along this direction, because this is plus Q, so it will be away from the source charge, it will be along this direction. Now this is minus Q, so this towards the source charge, so it will be along also this body diagonal. So also we can write E2 equals to Q divided by 4 pi epsilon naught 4 times of root 3 divided by s square into minus I cap minus j cap minus k cap. So this will be the electric field equal of E2 Q2. Now according to superposition principle, if you want to calculate net electric field, what you have to do? You have to add them together. So therefore the net electric field at the center of the cube, E net, is equals to the sum of these two forces, E1 electric field E1 plus E2. So what will be the summation of these two vectors? It will be simply 448, so minus 2q divided by 3 into root 3 pi epsilon naught s square, and then I cap plus j cap plus k cap. I cap, j cap plus k cap. They are also same as you can write x cap, y cap, j cap, or you can write I cap, j cap, k cap. And that you can write x cap, y cap, z cap, or you can write I cap, j cap, k cap. Both are actually same. So in this case, what will be our correct answer? Correct answer will be option C. Correct answer will be option C. So option C correct answer. Okay, good. Now take a look on question number 5. So in question number 5, it is written for an infinitely long wire with uniform linear charge density lambda along the z-axis. The electric field at a point A0, AB00, AB0, that is on the xy plane, away from the origin, is given by. Okay, so let me draw a figure first here. Let's say this is y-axis, this is x-axis, and this is our xy plane, and this is z-axis. This is z-axis. Now a charge carrying infinitely long charge carrying wire is placed along the z-axis. Along the z-axis, which is carrying a linear charge density lambda per unit length. This x-axis, this is y-axis, this is z-axis. Now what we have to do, we have to calculate AB0. That's mean on the point will be on this xy plane. And what is the coordinate of this point? AB0. So at this point we have to calculate electric field. So in last class we have learned, if we have an infinitely long wire, infinitely charge carrying long wire, and if we want to calculate a electric field at a perpendicular distance r from this wire, then what will be the value of this electric field? The magnitude will be lambda divided by 2 pi epsilon naught r, and directions will be always perpendicular to the length, and it will be away from the wire if the charge on the wire is positive. If charge is negative, then it will be towards the wire. So in this case, it will be away from the wire because it's positive charge. And if we write this is r cap direction, then will r cap. R cap. Or what we can write, if we write just multiply with r numerator and denominator, then what we'll get? We'll get lambda divided by 2 pi epsilon naught r square into r vector. R square into r vector. Then what is this r vector? R vector, that is the position vector of this point with respect to this point. So if we want to calculate any arbitrary point, if we want to calculate electric field at any arbitrary point because of infinitely long charge carrying wire, so what we have to do, we have to draw a perpendicular line from this point on the wire, and then we have to find out what will be the coordinate of this point. Once you know the coordinate of this point, then you can write what will be this position vector r. So once you know this position vector r, then you can calculate magnitude, and then if you put the value of these things here, you will get the electric field. So in these questions also we have a infinitely charge carrying long wire, and we have to calculate electric field at this point. So from this point, if we draw a perpendicular line on the wire, so it will be goes like this, so it will go like this, and it will cut the wire at the origin. So in this case, the coordinate where this line will cut the wire, it will be 0 0 0, and we know the coordinate of this point. So what will be our r vector? That is the position vector of this point with respect to this point. So in this case, our r vector will be a I cap plus b j cap, b j cap. So we know the r vector, we know the charge per unit length lambda. So what we have to do, then we have to put the value of this r in this equation. So what will be then our net electric field in this case? E will be lambda divided by 2 pi epsilon naught. So magnitude of this r will be actually mod of r in this case will be under root of a square plus b square. So square of this means a square plus b square, and then r vector. R vector in this case it will be along ai cap plus bj cap. ai cap plus bj cap. So this will be the net electric field at the position 0 AB 0 0. AB 0 0. So which option will be the correct answer in this case then? In this case, option B will be the correct answer. Option B will be the correct answer. Lambda divided by 2 pi epsilon naught a square plus b square ai cap plus bj cap. So in this case, ex cap, ey cap, they are actually the same vector. You see here, ex cap, ey cap, ez cap, they are the unit vector in Cartesian coordinates. So either you can write I cap, j cap, and k cap, or you can write ex cap, ey cap, ez cap, or you can write simply x cap, y cap, z cap, all are actually same. Okay, so correct option will be option B. Very good. Then in question number 6, what is written here? A segment of a circular wire of radius r extending from 0 to pi by 2 carries a constant linear charge density lambda. The electric field at the origin is. I think already we have solved this problem in last class. So I will request to you just check the last video. Lecture number 8. There you will find the solution of this question. What will be the correct answer? You can simply say correct answer will be option A. Option A will be correct answer. Okay. Then take a look on question number 7. So in question number 7, it is written a charge per unit length on a circular wire of radius A in xy plane with center at the origin is lambda equals to lambda naught cos theta, where lambda naught is constant and theta is the angle is measured from the positive x-axis. The electric field at the center of the circle is. Okay. So usually we have also solved the electric field at the center of a uniform charge carrying circular loop, and we have noticed that the electric fields is 0. But when it is non-uniform charge distribution, see here in this case lambda is itself function of theta. So in this case this lambda is actually non-uniform. At different value of theta, lambda will be different. So for non-uniform charge distribution, it may or may not be 0. So in this case we have to calculate. So we cannot use the standard result that we have already discussed in last class. So electric field at the center of a circular loop will be 0 only when, or it will be always 0 only when the charge is uniform. If it is non-uniform, then it may be 0, may not be 0. That depends on the charge distribution. So in this case, let me just draw a circle. So it is written the circle lies in the xy plane. So let's say this is y-axis and this is x-axis. Y-axis and x-axis. Center of the circle is at the origin. So this is the center of the circle, and this lies at the, this is exactly at the origin of this coordinate system. Now consider a point on the circle. So at different point charge density will be different. So at this point, if we say this angle is theta, then at this point the charge density per unit length will be lambda naught cos theta. So if you put theta equals to 0, at this point it will be lambda naught. If you put theta equals to 90, at this point theta will be 0, cos theta cos 90, so lambda will be 0. At this point it will be minus lambda naught. So at different point charge density will be different. So this charge distribution actually non-uniform charge distribution. Non-uniform charge distribution. So for this case, if we want to calculate electric field at the center, then what we have to do? We have to use the concept of electric field because of linear charge density. So for that, what we have to do? First, we have to consider this point. So already we have considered this point. What will be the coordinate of this point in terms of polar coordinate? We can write simply a theta, But if we want to write in terms of rectangular coordinate, that we can write a cos theta and a sin theta. Okay, a cos theta and a sin theta. And then we have to consider elementary length. So in this case, consider elementary length. What we have to do, we have to increase the value of theta. So when you increase the value of theta, elementary length will be generated at this position on the periphery of the circle, and this is called elementary length. So in this case, elementary length will be a d theta. A d theta. So now we know the elementary length. We know per unit length lambda is lambda naught cos theta. So what will be the electric field at the origin or at the center of the circle because of this elementary length? So the electric field at the center of the circle is E is equals to 1 by 4 pi epsilon naught. And then what we have to write? We have to write charge per unit length, charge on the elementary length. So lambda into dl. So in this case, lambda is equals to lambda naught cos theta, and elementary length a d theta divided by r cube. So what is r in this case? The position vector of the center of the circle with respect to this coordinate, a cos theta and a sin theta. So then what will be this r vector? In this case, r vector will be minus a cos theta I cap minus a sin theta j cap, and then cube of this magnitude of this r vector. So in this case, it will be a cube. And then what we have to do, we have to integrate. If we want to calculate net electric field at the center because of whole circle, then we have to integrate over the periphery of the circle, and for that limit of theta will be 0 to 2 pi. So now what we can do, we can little simplify this thing, and what we'll get a square. So we can write 1 by 4 pi epsilon naught a, and lambda naught also we can take outside, it is constant. And then remaining term, what we'll get minus cos theta, fact cos square theta I cap, and then minus sin theta cos theta j cap, and we have to integrate this term with respect to theta over the limit 0 to 2 pi. 0 to 2 pi. And from the integration concept, you can say that the product of this sin theta cos theta, the integration of the product of sin theta cos theta over the limit 0 to 2 pi will be always 0. The integration of this term will give us 0. So you have to integrate only this term. And when you integrate a cos square theta over the limit 0 to pi, what we'll get? We'll get pi only. Pi. So from integration part, what we'll get only pi. So if we put the value of this integration, then what will be the correct answer? So we'll get minus lambda naught divided by 4 pi epsilon naught a. So this minus sign I put it here, and then limit integration of the cos square theta over the limit 0 to 2 pi will give us pi, and then I cap. So pi will cancel out. So finally what we'll get minus lambda naught 4 epsilon naught a I cap. A I cap. That will be our correct answer. So option A will be the correct answer in this case. Option A will be the correct answer. Minus lambda naught 4 epsilon naught a I cap. Okay, good. And take a look on question number 8. So what is written in question number 8? In the figure, shown the electric field at the center of the semicircle is. So what has been written in this question, let's say we have a semicircle like this whose center is at the origin of the coordinate system, and a radius of this circle, let's say a radius of this circle is a. Then 1/4 part of the circle is carries plus lambda charge and another quarter part of the circle is carrying minus lambda charge. Then what we have to do, we have to calculate electric field at the center, that's been at the origin here. It's a O point. We have to calculate electric field at point O. Okay. So in this case, you can see that the charge over this first quarter part, from here to here, everywhere is same, plus lambda, and in second quarter part everywhere is minus lambda. So each quarter part have a uniform charge distribution. So for this type of situations, we can use the standard result that we have already discussed in last class. So what we have noticed, that if we have a charge distribution like this, let's say this is x-axis and this is y-axis, and if we have a quarter part of a circle and charge per unit length, the charge per unit length is lambda, and if the radius of this arc is capital R, then we have already calculated this electric field at the center of this arc part will be lambda divided by 4 pi epsilon naught r square. No, it's not r square, in r, and then minus I cap minus j cap. So when you calculate magnitude, so what we have noticed, that the magnitude will be root 2 times of lambda divided by 4 pi epsilon naught r. 4 pi epsilon naught r, and the directions will be actually since this charge is source charge is positive, so electric field will be along this direction. So it will make 45 degree with the negative x-axis, also it will make 45 degree with the negative y-axis. Okay. So in that case also, in this case also, we can use this result directly because it's a uniform charge over this length. First quarter part is a plus lambda and second quarter part is a minus lambda. So each part carries a uniform charge density here. So what we can do, we can think that this semicircle is made by 2/4 part of a circle, and 1/4 part is carrying charge per unit length plus lambda, and another quarter part is carrying charge per unit length minus lambda. So then what will be the net electric field at the center? So let me again draw this figure. So this is x-axis and this is y-axis, and we have a semicircle like this. This is the center of the semicircle, and so what we have to do here, on this part we have plus lambda charge. So from the concept that we have already learned in last class, from there we can say that the electric field, because of this part, will be along this direction. Will be along this direction. And what will be the magnitude of this electric field? It will be root 2 lambda divided by 4 pi epsilon naught r. 4 pi epsilon naught r. And then what will be the electric field because of second part? Because now second part have a linear charge density, uniform linear charge density, and it's minus lambda. So this was plus lambda and it's minus lambda. So from this figure we can see that if positive charge create electric field along this direction, so if there was a positive charge on the second part, then electric field would be like along this direction. But in this case, On the second part, we have actually negative charge density. So magnitude will be same like root 2 lambda divided by 4 pi epsilon r, but the directions will be along this direction. Directions will be along this direction. So again, it will make 45 degree with the negative x-axis in this direction. And in this case, radius of the circle is a, so you have to replace this capital R by small a. Okay. So now you see we have electric field, two electric field. For this part, we have electric field along this direction, and for this part, electric field along this direction with same magnitude. So what will be the net electric field then at the origin? For that, we have to decompose this to electric field. So if we decompose this electric field to orthogonal component, then one component will be along positive y-axis and another component will be along negative x-axis. And same way, if we decompose this electric field into two orthogonal components, then one component will be along minus y-axis and another component will be along minus x-axis. Minus x-axis, and this angle is also 45 degree and this angle is also 45 degree. So in this case, we can say that these two components will cancel out each other. The net electric field will be minus I cap direction. Minus I cap direction. So what will be the net electric field in this case? Net electric field will be cos 45 of this electric field and into 2 times, because one component will come from this part and one component come from this part. So we'll get 2 into root 2 times lambda divided by 4 pi epsilon naught a and then cos 45. Okay, cos 45. Now cos 45 is root 2, 1 by root 2. So root 2 will cancel out and 2 will cancel out. So what we'll get? We'll get lambda divided by 2 pi epsilon naught a. 2 pi epsilon naught a. And what will be the directions of electric field in this case? What will be the directions of electric field? It will be along this direction, minus I cap direction. So it will be along this direction, minus I cap. So we can write minus I cap here. Okay. Minus I cap direction. Okay, so in this case, net electric field, some mistake, let me write it minus I cap. So correct option in this case will be option A. Okay, so if we have a semicircular part like this, one part is plus lambda, another part is minus lambda, or if you have a 3/4 part of a circle and each part is carrying like plus lambda, minus lambda, plus lambda, in that case again you can use the standard result. You can use the standard result and then you can decompose this electric field and you can easily calculate what will be the net electric field. Okay, good. And then question number 9. So in question number 9, it is written, consider a long wire carries a linear charge density lambda is placed in the xy plane as shown in the figure. The net electric field at point 34. Okay, good. So in this question, this is x-axis, this is y-axis, and we have a infinitely charged carrying long wire. So this is the infinitely charged carrying long wire. So because of that, we have to calculate electric field at a point 34. At this point, we have to calculate electric field. So again, we have a infinitely long wire, and so for that we have to calculate the electric field. So we have, in last class we already discussed that if we have an infinitely long wire, then if we want to calculate electric field at a perpendicular distance r from this wire, then we can simply write that the magnitude of this electric field will be lambda divided by 2 pi epsilon naught r. where r is the perpendicular distance of this point. Let's say this is an infinitely long wire. We want to calculate at this point, so this will be the r. Okay, so if we know the perpendicular distance of this point from the wire, then we can write the electric field at this point. Magnitude of electric field at this point will be lambda divided by 2 pi epsilon r. So in this case also we have this wire. We know at what point it intersects the y-axis and which point it intersects the y-axis, as well as which point it intersects the x-axis. We know that these 2 points. So for this wire we have to calculate electric field at this point. So that's when we will use this definition, and if we want to use this definition, then what is unknown here, we have to only just find out the value of r. So what is r here? R is the perpendicular distance of this point from the wire. So let me draw a perpendicular line from this point. Okay. So this perpendicular distance, so in this case this is our r. So we have to calculate this value of r here. Value of r here. So how we can calculate this value of r here? For that, first we have to write the equation of the straight line. Equation of the straight line. So the equation of the straight line is, so we can write x divided by the intersect point of x plus y divided by the intersect point on y-axis. So 3 equals to 1. So from there what we'll get a 3x plus 4y minus 12 equals to 0. So this is the equation of straight line. So now if we want to calculate the perpendicular distance of this point 34 from the straight line, so if we want to calculate a perpendicular distance of any point from a straight line, what we have to, what we know some definition. Let's say, let me write just any arbitrary straight line. Let's say ax plus by plus c, this is equals to 0. So this represents a straight line. And now if we want to calculate the perpendicular distance of the point AB from this straight line, so what will be that perpendicular distance? So perpendicular distance, let me just write it as a d. So d will be, so we have to replace this xy by this coordinate. So we'll write a into small a plus capital V into small v plus c divided by under root of coefficient of x square plus y square, that is capital S square plus capital B square, and distance will be always positive, so we have to take mod. So this will give the perpendicular distance of this point from the straight line. So if we use the same definition here, this is our equation of straight line. So in this case capital A is 3, capital V is 4, and C is minus 12. So we have to calculate the perpendicular distance of the point 34. So in this case a small a is equals to 3 and capital small b is equals to 4. So then what will be the perpendicular distance of the point 34 from this straight line? So the perpendicular distance of the point 34 from the straight line (3x plus 4y minus 12 equals to 0) is r is equals to mod of 3 into 3 plus 4 into 4 minus 12 divided by under root of coefficient of x square, so that is 3 square 9 plus 4 square 16, and mod of this will give us 3 plus 9, so 16 minus 12 4 39. So this will give you 13 divided by 5. So perpendicular distance of this point from the straight line is 13 by 5. So then what will be the electric field? So the magnitude of electric field at 3, 4 will be simply lambda divided by 2 pi epsilon naught into r, and then put the value of r, this 5 by 13 by 5. So what will get? 5 lambda divided by 26 pi epsilon naught. 26 pi epsilon naught. So this will be the magnitude of electric field at point 3, 4 because of this infinitely long charge carrying wire. Yeah. So in this case, correct option will be option A. Option A is correct. Okay. So now take a look on question number 10. So in this question, it is written a semi-infinitely line charge of linear charge density lambda has the shape as shown in the figure. The portion ABC is 3/4 part of a circle of radius r. Okay. So from A to C, this portion is a 3/4 part of a circle of radius r. Okay, radius r. And then what has been asked r, well, the state portion from C to infinite. So the state portion, this portion, C to infinite portion, and it is parallel to AOP. So it is parallel to this line. Okay. Now what has been we have to calculate the electric field at the center of the circle. At this point, you have to calculate the net electric field. Net electric field. So again, in this case, if you take a look on the figure carefully, what you will see here. Let me just draw this line here. So it's a 3-part of circle. So one part is this. 1/4 part of circle is this part. And the next quarter part this is the next quarter part. Next quarter part, and again we have this is the last quarter part of this circle. So this is the last quarter part of circle. So now you can see that this quarter part and this quarter part circle, they will create a same amount of electric field at the center. They will create same amount of electric field at the center, and the directions of electric field will be opposite to each other. This field, this portion, first portion, this portion will create electric field along this direction, and this portion will create electric field along this direction. So they will cancel out each other. They will cancel out each other. Then what will be the electric field? Only this portion and this semi-infinite portion. Semi-infinitely long wire. And now we know the electric field, what will be the electric field because of semi-infinitely long wire that we have already discussed in last class. So let me write it again here. So if we have a semi-infinitely long wire like this, and if it is carrying charge per unit length is lambda, then if we want to calculate at one end at a perpendicular distance r from the wire, then what will be the magnitude of this electric field at this position? E will be √2 lambda divided by 4 pi epsilon naught r. This will be the magnitude at this position. And what will be the direction? If we do a perpendicular line like this, then the net electric field will be max 45 degree with this line. And 45 degree with this line. Good. And also, if we have a semicircle, a quarter part of a circle like this, and if the circular part have radius r, and if it is carry charge per unit length lambda, and for this case also we have, if we calculate the electric field at the center, what will be the magnitude of this electric field? Magnitude will be root 2 times, sorry, there will also be lambda, 2 times lambda divided by 4 pi epsilon naught r, and if it is positive charge, then electric field will be along this direction. Electric field will be along this direction. So if we draw a negative y-axis, negative x-axis, then it will make 45 degree with the both axes, negative x-axis and negative y-axis. Okay. So if we put these two results here in this figure, what we'll get here, that this semi-infinite state portion, that is from C to infinite, because of this portion, the electric field will be along this direction. Electric field will be along this direction. And in this case, the distance of the center from this straight line, perpendicular distance of this center O from the straight line will be r. So electric field, magnitude of this electric field will be root 2 lambda divided by 4 pi epsilon naught r. Okay. And also this curve portion, quarter portion of this circle, it will also create a same amount of electric field, and directions of this electric field will be along this direction. This direction. So again, they will also cancel out each other. They will also cancel out each other. So what will be the net electric field then? The electric field because of this portion will be cancelled out by this portion. The electric field because of this semi-infinite state portion will be cancelled out by this portion. The net electric field will be 0. Net electric field will be 0. So correct option will be option C. Correct option will be option C. Good. Then take a look on question number 11. So what has been said, written in question number 11? Two alpha particle passes rapidly through the exact center of a hydrogen molecule, moving on a line perpendicular to the internuclear axis. The distance between nuclei is b. Where on its path does the alpha particle experience the largest force? Assume that the nuclei do not move much during the passage of alpha particle. I'll also neglect the electric field of electron in each molecule. So we know hydrogen molecule is like H2. H2 means we have two hydrogen atom. So let me just draw two hydrogen atom here. One hydrogen atom here, another hydrogen atom here. So these are the nucleus of each hydrogen atom. So there will be one proton each nucleus. No hydrogen atom doesn't have any neutron in its nucleus. So there will be only one proton. So one proton here, another proton is here. So let me just write PP. Both have positive charge P. And now the distance between these two nucleus, it is written in questions, is B. Distance between two nucleus is B. And now what has been said, कि alpha particle passes through exactly the center of the hydrogen molecule. So this is the center, and let me draw a straight line. It will passes through the center and perpendicular to the internucleus axis. Now in this path, if a charged particle, alpha particle means H double plus. If this alpha particle move along this line, so what has been asked, on its path, that is along this path, where does this alpha particle experience the largest force? Okay, so I have to tell at what position of this alpha particle along this line experience the maximum force because of these two photon. Because of these two photon. So this logic also we have already discussed in last class. Let me just correlate this concept. When we have a uniform charge carrying circular loop, we have calculated electric field on the axis of the circular loop, where we have noticed that if the radius of this circular loop is r, and it is carrying lambda charge per unit length, then total charge on this loop will be q is equals to 2 pi r lambda. And because of this charge, if we calculate electric field on the axis at a distance z from its center, and that electric field, we have noticed that electric field will be qz divided by 4 pi epsilon naught r square plus z square whole to the power 3 by 2. 3 by 2. If it is on the above the loop, then it will be along this direction, and if it is below the loop, then electric field will be downward. Okay. And then we have also noticed that this electric field will be maximum for z equals to r by root 2. So on the axis, at this point, electric field at a distance z equals to r by root 2, that electric field will be maximum. Now, similar electric field also will get if we place more than one charge on a circular loop symmetrically. Okay? Let's say this is a circular loop of radius r. Now, if we place n number of point charge on this circular loop, symmetrically. Symmetrically means the angle between any two charges must be equal. Like if this two charge angle is theta, then if we place the next charge here, the angle between these two charges will also be theta. The angle between these two charges will also be theta. The angle between these two charges also be theta, and the angle between these two charges also be theta. Okay. So like this. So if we place more than one charge, let's say two charges, three charges, or four charges, or n number of point charges where n is greater than 1, 2, 3, 4, 5 up to infinite. And if all the charges are identical, and if we place them symmetrically on this circle, and then if we calculate the electric field on the axis of this circle at a distance z from its center, we'll get exactly same electric field like here. Same electric field as we have noticed for the loop, charge carrying circular loop. So one thing will be changed here. So here q is the total charge on the loop. So here also we have to write, let's say we have n number of point charge, then what will be the electric field at this point? This electric field will be E is equals to n, and if each charge is q, then what will you write? Total charge on this loop will be now n into q. N into q. Then if this distance is z, then it will be z divided by 4 pi epsilon naught r square plus z square whole to the power 3 by 2, where n should be greater than 1. So at least n should be 2, 3, minimum value of n should be 2. So if you have a 2 or more than 2 charges, and if all the charges are identical, and if we place them symmetrically means the angle between any two charges must be equal. If that is the case, then the axis of this circular loop at any point electric field will be this nqz divided by 4 pi epsilon naught square z square. Now, if we draw this electric field variation, it will be exactly same variation as we have noticed for the circular loop. So in this case also we can say, because of this charge distribution, the electric field on the axis will be maximum when z equals to r by root 2. Z equals to r by root 2. So now if I throw a charge particle along the axis of this loop, so it will experience the maximum force where the electric field will be maximum. Electric field will be maximum. So if we throw a charge particle any external electric field E, Then if the charge particle have charge q, then the force on this charge particle will be q into capital E. So in this case, if we throw alpha particle, now these two proton, nucleus of hydrogen atom, that is proton, they will create electric field along this axis. So because of this electric field, this alpha particle experience a force. So this force will be maximum where this electric field along the axis because of these two charge will be maximum. So now compare this result with this result. What we can do here, we can also draw a circle taking the radius b by 2, that is center of this circle will be at the center of this two nucleus, a midpoint of this two nucleus. So we can see that this two nucleus will be lie on the circle of radius b by 2. And now if we want to calculate electric field on the axis of this loop, it will be like this, where we have to replace this n by 2 because now we have two proton, 2 into q, and electric field will be variation exactly same. Okay, so at what point on the axis electric field will be maximum, and the value of z will be root 2 times radius of this the radius of this loop is b, then electric field at this point will be b by root 2. But in this case, what will be the radius of this circular loop? The internucleus distance in question it is written internucleus distance is b, that is the distance of these two nucleus is b. So then what will be the radius of this loop? Radius will be b by 2. B by 2. So now for what value of z the electric field will be maximum on the axis of this loop? So electric field will be maximum when z is equals to 1 by root 2 times of radius. So in this case radius is b by 2, so 1 by root 2 times b by 2. At this position on the axis electric field will be maximum. Electric field will be maximum. So if electric field is maximum, then alpha particle will also experience a maximum force. Alpha particle will also experience a maximum force. So F will be maximum. F will be maximum when Z will be this. Z will be B by 2 root 2. So we can write it in this way, B by 2 root 2. B by 2 root 2. Okay. So I hope you got the idea. So what is the idea here? If we have already calculated electric field on the axis of a circular loop, and we have noticed that electric field will be qz divided by 4 pi epsilon r square plus z square all to the power 3 by 2. Now instead of uniformly charge carrying loop, if we have a discrete point charge where the number of charges more than one, let's say 2 charges, 3 charges, minimum should be 2, but it could be up to infinite. So if we have a n number of charges where n is greater than 1 and all charges are identical, and if we place them symmetrically on the circular loop, then the electric field on the axis also can be written as in this pattern, nqz divided by 4 pi epsilon r square plus z square. Okay, so in this case also, if we want to calculate at what point on the axis, at what distance on the axis electric field will be maximum, so it will give you the same result where we have as we have calculated for the circular loop, because the electric field is variation exactly same. The electric field variations for this case and this case with respect to z is exactly same. So as we have noticed for the circular loop that electric field will be maximum on the axis at z equals to r by root 2. So in this case also it will be electric field will be maximum when this z will be, the value of z will be r by root 2. So now what we have done here, we have two proton here and here. So now we have drawn a circle of radius b by 2, so that the charge 2 proton will lie on the circle symmetrically with each other. So now if we want to calculate the electric field on the axis, it will be exactly same like this, only we have to change this n now will be replaced by 2, and this q will be the charge of each proton. But if we look the variations of electric field, it will be like same. So now if we throw a charge particle along this line, now this charge particle will experience a force q into E, where this electric field will be because of these two charge on the line, that is on the axis of the loop. Now when this electric field will be maximum, then only this alpha particle will experience a maximum force. And at what positions of z this force will be maximum? When z will be 1 by root 2 times of the radius. So 1 by root 2 times, in this case radius is b by 2, so z will be b by 2 root 2. So at this position electric field will be maximum, so the force on the alpha particle will also be maximum. So correct option will be option B. Correct option will be option B. Good. Okay, now take a look on question number 12. In question number 12, it is written that 3 charges are located on the circumference of a circle of radius r as shown in the figure below. 2 charges Q subtend an angle 90 degree at the center of the circle. The charge Q is symmetrically placed with respect to charges Q. If the electric field at the center is 0, then what is the magnitude of capital Q in terms of small q? Okay, so what has been written here, let's say we have a circle of radius r, and then we have these 3 charges on this circle. These 2 charges are capital Q and another charge is small q. Now the angle between these 2 charges R, capital R, and this is the small q charge is placed here, and it's said that this charge is placed symmetrically with respect to capital Q. So these 2 angles are actually same, and these 2 angles are same. So what we have to do here, we have to calculate the value of capital Q in terms of small q, so that the net electric field at the center is 0. Net electric field at the center is 0. So what we can do here, so first calculate the electric field. So again we have 3 charges here, capital Q, 2 capital Q and small q, and the net electric field will be 0. So what you can see here from this figure, let me draw this figure again here. So this is the circle and this is the center of this circle. Now we have placed 2 charges plus q charges, so that they makes an angle 90 degree with each other at the center, and exactly symmetrically with these 2 charges we have placed another charge small q here. And what has been written here, the net electric field at the center is 0. Then what will be the value of capital Q in terms of small q? Okay, so what we can do here, we can simply write the electric field because of this 2 capital Q charge. So what will be that electric field? If this radius is r, then the electric field of capital Q along this direction, and electric field because of this capital Q charge will be along this direction. This direction. And what will be the magnitude of this electric field? Both of the electric field will be E is equals to capital Q divided by 4 pi epsilon naught r square. Epsilon naught r square. Now both of this electric field, since this angle is 45 degrees, so the angle between these 2 electric field will also be 45 degree. So now what we can do, we can decompose this electric field into 2 orthogonal components. One component will be along this, another component along this direction. Also we can decompose this electric field. One component will be along this direction, another component along this direction. Now these 2 components will cancel out each other. So net electric field will be along this direction. So because of these 2 charges. And now the net electric field at the center will be 0 only if this charge create an electric field along this direction. Along this direction, then only the net electric field will be 0. So when this charge will create electric field along this direction if this charge is positive. If this charge is positive, then only it will create electric field along this direction. Okay, so now we have to calculate what will be the magnitude of this electric field. So for that, what we can do, we can simply write that the electric field because of this small q at the center will be equal to the electric field because of these two capital Q charge. Okay, so let me write here the electric field at the center will be 0 when the electric field because of Q1 at the center, what will be that electric field? 1 by 4 pi epsilon naught Q divided by R square is equals to the net electric field because of these two charges. One to the net electric field, 2 into electric field because of individual charge, capital Q, that is 4 pi epsilon naught R square, and into cos 45. Okay. So from there, what we can write, 4 pi epsilon naught R square will cancel out each other. So it will get Q is equals to cos 45 is 1 by root 2. So root 2 times into capital Q. Now we have to calculate the value of capital Q in terms of small q. So what we can write, capital Q is equals to Q times divided by root 2. So in this capital Q will be Q times divided by root 2 or 1 by root 2 times of Q, and that time the net electric field at the center for this charge distribution will be 0. So correct option will be option A. Correct option will be option A. Good. Then in question number 13, what is written here? The two long linear charges having a charge density lambda and minus lambda are joined at one end at right angle as shown in the figure. The electric field at point P. Okay. So from here to here up to infinite, this portion is carrying a minus lambda charge per unit length. And from this point to up to this direction infinity, this portion is carrying a plus q charge per unit length. Then what has been asked, what will be the net electric field at point P? Net electric field at point P. So let me rewrite this figure again here. Redraw this figure again here. So this part is semi-infinite part, and another part, this part is also semi-infinite part. This part is carrying charge per unit length lambda, and this part is also carrying charge per unit length minus lambda. Then what has been asked, the angle between these two is 90, and we have to calculate electric field at this point P, where the distance of this P point from this intersect of these two lines is R. So at this point we have to calculate net electric field because of these two a linear portion. Linear portion. So what we can do here, again we can use the superposition principle. We can calculate the electric field at point P because of only this portion and only this portion, and then we have to take the vector sum. So if I want to calculate, let me just write a name, let's say O, A and B. So once we have to calculate electric field at point P because of OA portion, and next time we have to calculate electric field at point P because of OB portion. Now if we want to calculate electric field at point P because of OB portion, so what will be that electric field? Let's write here the electric field the electric field at point P due to OA part. What will be that electric field? So in this case, you can see the P point actually lies on the axis of this charge carrying wire. Charge carrying wire. So already we have also calculated electric field for this type of cases. So what will be the electric field? Let me write as a E1. So E1 will be 1 by 4 pi epsilon naught. Charge per unit length is lambda, and then will be 1 by R minus 1 divided by R plus length. So in this case, length of this wire, that is from O to A, it will be infinite. OA portion length is infinite. This. And so what will be the magnitude of this electric field then? This part will give us 0. So if this is 0, then it will be simply lambda divided by 4 pi epsilon naught R. And 1 by 4 pi epsilon naught we can write in terms of Coulomb constant, that is K. So K lambda divided by R. So this will be the electric field. This will be the electric field along which direction? Along at point P, because of this OA line. Now this OA line have positive charge, so in this case electric field will be downward, O to P. Okay, so electric field will be along this direction, O to P direction. Okay. Now if we want to calculate electric field due to OB portion, this again we know that this is we have like a semi-infinitely long wire, and we have to calculate electric field at a distance R from at a perpendicular distance R from it one end. So right, electric field at point P due to OB portion, the OB part is, let's say, E2. If I write E2, then what will be the value of E2? E2 will be, in this case, see, it's a negative charge. Charge per unit length is lambda. So what we have noticed that if we have an infinitely long line per this, and if we want to calculate electric field at this point, the charge per unit length is lambda, then we have noticed that electric field along this direction. But if it is negative charge, then electric field will be along this direction. And what will be the magnitude of this electric field? It will be lambda divided by 4 pi epsilon naught R into root 2. R into root 2. And then if we want to write 1 by 4 pi epsilon naught K, 1 by 4 pi epsilon naught in terms of K, so Coulomb constant. So we can write K lambda root 2 divided by R. This will be the electric field at this position. So same definition also we'll use here. So if we use the same result here, then what we'll get? So it will get here, the electric field at point P, because of this OB line, it will be K lambda divided by R into root 2. R into root 2. So this will be the electric field, and which directions it will be? If we draw a parallel line in this case to the wire, it will make 45 degree with this line. So along this direction, so this will be the direction of electric field E2. So this is the directions of electric field E2, and this is the directions of electric field E1. Now what we have to do? We have to take the vector sum of these two electric field. Vector sum of these two electric field. So for that, what we can do, if we just decompose this electric field to orthogonal component, we know in this case this will be 45 degree. So what will be the component along this direction, and another component will be along this direction. So we know the magnitude of E2, we know the angle, this angle 45 degree. So the component along these directions will be E2 cos 45. So what give you that value? This will give you k lambda divided by r. K lambda divided by r. And also if this angle is 45, so along this direction component will be E2 sin 45. Sin 45 is also 1 by root 2. So again this component will also be k lambda divided by r. K lambda divided by r. And also you see the magnitude of E1 is also k lambda r. So that's mean this component and this component will cancel out each other, and net electric field will be along this direction. And what will be the net electric field? Net electric field will be this much, k lambda r. K lambda r. So net electric field in this case, E net will be vector sum of E1 plus E2. So when you take sum of these two components will cancel out each other, and net electric field will be k lambda divided by r. K lambda divided by r, and it will be parallel to OB, or in this case we can write PB. PB direction. Sorry, if we write PB it will be wrong. Let's from the figure you can understand it will be along this direction. It will be along this direction. So it will be parallel to OB. OB is along this direction, so it will be parallel to the OB. And magnitude will be k lambda by r. K lambda by r. So correct option will be option A. Correct option will be option A. Okay. So in this case we have used two concepts. One is electric field at a perpendicular distance, and first case we have electric field on the axis of the charge carrying wire. And both the cases we have already discussed in class, so we have used the standard result that we have discussed in our last class. So this is the electric field on the axis when we calculate the electric field at point P because of OA portion. So in this case P point will lie on the axis of this charge carrying wire, and if we want to calculate electric field because of OB portion at point P, that P point will be at a perpendicular distance r from the semi infinitely long wire. So we have used these two ideas here, and from there we have calculated electric field separately, and then if we added these two electric field, and when you added these two electric fields, so either you can add vector or you can just decompose them. So when you decompose them, from there we can notice that this electric field will be cancelled out by this component of this E2. So net electric field will be along this direction, and what will be that value? K lambda by r. Okay, good. Then take a look on question number 14. So in question number 14 it is written that a electron revolve around a long line charge of density lambda under the effect of electrostatic force as shown in the figure. The kinetic energy of the electron is. Okay, good. So what is written here? We have a charge carrying infinitely long wire. So this is a charge carrying infinitely long wire. Now because of this charge it will create an electric field here, and in this electric field, because of this electric field there will be a force on the electron. So this force will be towards the in this case electron have negative charge, so force on this charge will be minus q into E. So force will be, let me just draw right here. So this is a charge carrying long wire. So let's say this is a point, certain point, or let me draw a circle here, circle like this. So now if a charged particle rotate in a circle, or any particle if it is rotated in a circle, then there must be two forces. One force will be towards the center and another force it will be away from the center. So in this case force towards the center will be because of the electrostatic force. Because of the electrostatic force, because this charge carrying wire, it will create an electric field. Let's say radius of this circle is r. So electric field at this position will be lambda divided by 2 pi epsilon naught r. To r caps electric field along this direction. But since the charge electron itself a negative charge minus e, so the force on this force on the electron will be F is equals to minus E into electric field. So it will be opposite to the directions of electric field. So electrostatic force will be along this direction. Electrostatic force will be along this direction. And we know if any particle is rotated in a circular path, so with a uniform velocity, then there will also be a centrifugal force. And what will be that force? If the velocity, if we assume that the velocity of the electron is v, then centrifugal force will be mv square divided by r. mv square divided by r. So now if the circle is rotated, electron is rotated in this circle, then these two forces must be equal, electrostatic force and this centrifugal force. These two forces will be equal. So from there we can calculate what will be the kinetic energy of this electron. What will be the kinetic energy of the electron? So just write here. For equilibrium, force of on electron because of electric field is equals to centrifugal force mv square by r. So in this case, electrostatic force will be, magnitude of the electrostatic force will be E into electric field at this position because of this charge carrying wire. So that will be lambda divided by 2 pi epsilon naught r is equals to mv square divided by r. So r will cancel out from both sides. So what will get mv square? If we multiply with half on the both sides, then what will get? Half mv square is equals to E lambda divided by 4 pi epsilon naught. So this will be the kinetic energy of the electron. This will be the kinetic energy of the electron. So correct option will be option B. Option B will be the correct answer. Okay, good. Then take a look on question number 15. So in question number 15, it is written the charge Q is uniformly distributed over a thin half ring of radius r. The electric field at the center of this ring is. Okay. So this I will give you a hint. You can solve yourself. So let me just draw a semicircle here. Okay, this is semicircle of radius r, and then what has been set, what has been written here, that Q charge is uniformly distributed over this half ring. So that's when Q charge is distributed over this half ring, and uniformly means per unit length the charge density must be same everywhere. So that in this case we can write lambda is equals to Q divided by, what will be this length? Periphery of a semicircle of radius r, it will be pi r. Usually it is for a circle it is 2 pi r, for semicircle it will be pi r. Okay, pi r. So that is charge per unit length, and then what we have to do, we have to calculate electric field at the center. Electric field at the center. So either, as we have discussed, you can consider this superposition of two quarter part, and then you can calculate what will be the electric field using the standard result of each quarter part. So and then at finally what we have to do, you have to replace at lambda by this value Q divided by pi r. If you replace, then you will get the correct answer. Okay, I hope you can do it yourself. Let's do it. And then what is written in question number 16? A particle of mass m, charge q, is constant to move along the straight line joining the two other equal charges fixed at x equals to plus minus a. The time period of the small oscillation is. Okay, so let's say this is our x-axis. This is our x-axis, and this is x equals to 0. X equals to 0, and then x equals to plus a, x equals to minus a. So at this 2 point we have a 2 fixed charge plus q. 2 fixed charge plus q. And then what is said that a particle of mass m and charge q is constant to move along this line. So now charge, which is supposed to move along this two line, is placed at the center, initially at the x center q. Between these two charges, let's say at x equals to 0 we have placed another charge q, and charge of this, mass of this charge is m, and charge this particle is charge q. It is supposed to move along this straight line only. It is free to move, but it can move only along the straight line, that is along the x-axis. Along the x-axis. What has been asked, what is the time period of the small oscillation? Now the charge particle is placed along the line. There is no, I mean, in the question it is written where the charge is exactly placed. It is only written that it can move along this direction, and what we have to calculate, we have to calculate the time period of the small oscillation. So in this case, say if we place this charge somewhere here, so you can see the net force on this charge particle will be, so this charge will repulse this charge along this direction, and this charge will also repulse this charge along this direction. So net force along will be towards the left. So because of that, that charge particle will always always move along the left. So it will never come back towards right. So it will never give you a SHM motion. So we cannot calculate what will be the time period. So it will give a straight line motion, and time period of the straight line motion is infinite. But we have to calculate the time period of the small oscillation. That means this particle must execute a SHM motion. Then only we can calculate this time period of the small SHM motion. So for that, we have to place this charge particle between these two charges. Between these two charges. So let's say we have placed this charge particle at x equals to 0. At x equals to 0. So at this moment, you can see that this charge will apply a force on this charge that is placed at x equals to 0. It will be towards right, and the force will be q square divided by s square. And also this charge will apply a force which will be towards left, and the magnitude will be exactly same as the force is applied by this charge. So because of this, these two forces will cancel out each other. So if we place this charge particle at x equals to 0, it will remain fixed at this position. Remain fixed at this position. That's when x equals to 0 is the equilibrium position for this q charge, because of this other two charge distribution, by in presence of other two charge. Now if we give a small displacement of this charge particle towards any direction, either towards the left or towards right, so let me displace it towards right, this distance, where this distance is very, very small. This x is very, very small compared to the distance of this particle. This distance was a, so here x is much, much less compared to a. X is much, much less than compared to a. So now at this position, if we calculate the force on the charge particle, now you can see this distance will be less than a, and this distance will be greater than a. So because of that, now this the force on this particle q, because of these two charges now will not cancel out each other. So there will be net electric force, and because of that force, actually we can say that this distance now is less compared to this distance. So if you displace this charge particle towards right, the force that will act on this Q will be towards left. So we are displacing this charge particle towards right, but the force will try to bring back to the origin. The force that is acting on this charge particle, it will try to bring it back to the origin. So that's when the force is in this case acting on the motion opposite to the motion. So in this case, if we can show that this force on the particle and the force that is acting on the particle is proportional to the displacement, then we can say that this particle will show a SHA motion, and then we can calculate what will be the time period of this motion. So for that, let me just find out the force on the charged particle after displacement from x equals to 0. So the net force after displacement of the particle F can be written as let me first write force on this charged particle because of this charge. So it will be Q square divided by 4 pi epsilon naught, and what will be the distance between these two charges after displacement? It will be a minus x whole square. A minus x whole square. And what will be direction? Direction will be minus x cap. And then also calculate the force because of this charge. It will be Q square divided by 4 pi epsilon naught. Now the distance between this charge and this charge will be a plus x. A plus x. So a plus x whole square, and the direction plus x cap direction. Plus x cap direction. So now if we simplify this thing, what we'll get? We'll get Q divided by 4 pi epsilon naught. And then first write this term here. So what we'll get? 1 by a plus x ka whole square, and then minus 1 by a minus x ka whole square into x cap. Into x cap. So now this displacement, if we assume that this displacement is much less than compared to the distance here. So if we take common from this square bracket, what we'll get? We'll get a square here, and this bracket will give you 1 plus x divided by square. And also if we take common a square here, so what we'll get? Q divided by 4 pi epsilon naught a square. And inside the bracket, what we'll get? We'll get 1 plus x divided by a whole square minus 1 divided by 1 minus x divided by a whole square. Now this x by a, when x is much less than a, so x by a will be less than 1. So we can do the binomial expansion of this term. So for the after doing the binomial expansion, what we'll get here? 1 q divided by 4 pi epsilon s square, and if we take this term into the numerator, then what we'll get? We'll get a 1 plus x divided by a whole square minus power minus 2 minus 1 minus x divided by a power minus 2. Power minus 2. So this will give you q square divided by 4 pi epsilon naught s square, and this will give you 1 minus 2x divided by a, and this will give you minus 1 minus 1. Now this minus and this minus will be plus, so it will be 2x divided by. Okay, so when you simplify this thing, finally what we'll get? Minus 1 will cancel out, and this will give you minus 4x divided by a. So finally what we'll get? We'll get a minus q square divided by pi epsilon naught aq into x. Into x. So finally the net force on the charged particle after displacement, what we get here? minus q square, of course directional way. So minus q square divided by pi epsilon naught a cube, pi epsilon naught a cube into x and x cap direction. Okay. So you see here we have displaced this charge particle towards positive x cap, but the net force, you can see there is a minus sign, so the net force will be towards minus x cap, so it will be opposite to the motion of the particle. And these all terms, q square divided by pi epsilon naught a cube, these are constants, so it is proportional to x, that is displacement from its equilibrium position. So in this case particle will execute actually SHM motion. So if we want to write the equation of motion, then what we can write here, m mass into acceleration dx by dt square. So in this case this force, we have only x component, so x component will cancel out, so what we get here, minus q square x divided by pi epsilon naught a cube, pi epsilon naught a cube. And then if you divide it by the mass to this equation, to the right side, what we'll get here, we'll get dx square by d square x by dt square is equals to minus q square divided by pi epsilon naught a cube into m into x, m into x. So this is actually this term is constant here, so you can see that this is the differential equation of SHM motion. So in this case, you compare these equations with the standard equations of SHM motion, what will get, the standard differential equation of SHM motion is d square x by dt square is equals to minus omega square into x, where omega is the angular frequency of this SHM motion. So if we compare these two equations, what we can write, the angular frequency of SHM motion is equals to q square divided by pi epsilon naught a cube into m, So from there what will get, omega is equals to under root of q square divided by pi epsilon naught a cube into m. Then what we have to calculate, we have to calculate time period. Therefore the time period t is equals to 2 pi by omega. So this will give you 2 pi and then omega 1 by omega, so it will give you pi epsilon naught m a cube divided by q square, divided by q square. So this will be the time period of the small oscillation. So which option will be the correct answer? Okay, so we can a little bit simplify this term here. You can see that a cube, we can write a into a square, so we can take a outside of the square root, and also from denominator also we can, if q square, if you take it outside from the square root, it will give you q, so we'll get 2 pi a divided by q into under root of square root of pi epsilon naught m into a. Okay, so this will be our correct answer. So in this case you can see that correct option will be option D. Option D will be correct. Okay, option D will be the correct answer. Good. Okay, now in question number 17, so in question number 17 it is written 6 equal charges q are fixed at the corner of a hexagon of side a particle of mass m, charge minus q naught, and is released from a height z equals to from a height z such that z is much less than a above the center of the hexagon. The angular frequency of the oscillations of the particle about the center of the hexagon is. Yeah, good. Let's say this is a regular hexagon of side A, and then 6 point charges are fixed at the vertices of this regular hexagon. Each charge are q. Each charge are q. And after then, what has been said that if we release a point charge minus q along the line, the axis of this charge of this regular hexagon. Yeah. At a distance z, let's say this distance is z, such that this z is much less than a, where a is the side of this regular hexagon. That's when it will also be equal to the distance of the vertices from its center. Okay. So in this case, z is much less than a. Then what has been asked, the angular frequency of the oscillations of the particle around this and about the center. So in this case also, first we have to understand why this particle minus q charge, if we release this minus q charge from here, why this particle will execute SHM motion about this center of the circular loop, so center of the hexagonal loop. So you see, this 6 point charge will create electric field along the axis, and in this case, this all 6 charges are positive. So in this case, they will electric field along this direction, upward direction. Now, in this electric field, if we place a minus q charge, then force on this minus q charge will be downward because the charge is negative. So minus q into e, it will be opposite to the electric field. So this force will be downward. So we have force. We release this charge particle here, and there will be force on this charge particle downward. And at this moment, assume that there is no gravity. So it is not written in the questions, but there is in the option there is no z, so we can assume that there is no gravity. So because of this force only because of this q force, electric force q into e, this will move downward. Now when it will move to the downward, so there will be force, and because of that it will accelerate it, and because of that it will gain some kinetic energy. So the moment when it will reach at the center of this hexagon, at this moment the net electric field at the center will be 0. You can see this electric field, this charge will cancel out each other. This charge will also cancel out their electric field each other, and this charge will cancel out electric field each other. So net electric field will be 0, but this charge particle already gains some kinetic energy. Because of that, it will move downward. It will start move downward, and when it start moving downward, then you can see at the bottom side of this loop, the electric field because of this 6 charge will be downward. Now this charge particle is minus q, so force on this charge particle now will be upward. So because of this upward force, the particle velocity of the particle will now decrease at same distance at which we have released from the charge particle above the loop. When it travels the same distance below the loop, its kinetic energy again it will be 0. The moment its kinetic energy will be 0, it will be at rest. So but that time there will be a force in upward directions, and because of that this charge particle will start moving upward. So these motions will repeat with time, upward, downward, upward, downward, upward, down, upward, down. So this type of motion we call a SHM motion. Or you can say, in this case we can say periodic motion. And then if we can show that this force is proportional to z, that is displacement from the equilibrium, then it will be we can say that this motion will be SHM, and we can find out what will be the angular frequency. So for that, first what we have to do, we have to calculate electric field on the axis under this condition when z is much less than a. Now how we can calculate electric field? Already we have discussed just few minutes ago. If we connect this all 6 charge by a circle of radius r, like this, so what we'll see a 6 identical point charge are placed symmetrically on a circle of side a of radius a. 6 point charge are placed on a circular loop symmetrically, but the radius of the circle will be a. Then what will be the electric field on the axis of this circular loop? Electric field on the axis of the circular loop will be, if it is on the above this, and this is the z direction, z axis, so it will be 6q z divided by 4 pi epsilon naught z plus z square plus s square all to the power 3 by 2, all to the power 3 by 2, and directions will be along z cap. Directions will be along z cap. And now if we consider this condition that where z is much less than a, so under this limit where z is much less than a, so approximately we can write that z square plus s square is equals to s square, because z is much less than a. When we write that, then what we'll get 6q z divided by 4 pi epsilon naught into a cube, and directions will be z cap. Okay, z cap. Then if we know the electric field, now if we place the charge particle here minus q charge, so we can find out what will be the force on this charge particle. Therefore the force on the charge particle, the force on minus q is F is equals to minus q into E. So what will be the force? It will be minus 6q square z divided by 4 pi epsilon naught a cube. 4 pi epsilon naught a cube. So we can assume in this way also. So when the charge particle, if we charge particle released at the center of this loop, there will be no force because no electric field is there at the center. So net force will be 0. Charge particle will be remain at rest at this position. Now if we give a little displacement from its center along this axis by a distance z, and then if we release, so that means we are giving a displacement this charge particle upward direction, but the net force on the charge particle that will be that is minus z cap, that is downward, that is opposite to the motion, and it is also proportional to the displacement from its equilibrium position. Equilibrium position. So in this case also we can say that the particle will execute SHM motion, and what will be the equation of motion? M into, in this case we have displacement along, we have give the displacement along z direction, so we can write d square z divided by dt square is equals to minus 6q square 6q square into z, 6q square into z divided by 4 pi epsilon naught a cube. 4 pi epsilon naught a cube. So now if we divided this mass the both side, then what we'll get? We'll get d square z by dt square is equals to 6 q square divided by 4 pi epsilon naught a cube into m to z. Okay, so again this is a equation, differential equation of SHM motion. So if you compare with this equation with the standard equation, from there we can say the angular frequency, square of the angular frequency will be this term. So angular frequency will be under root of 6q square divided by 4 pi epsilon naught m a cube. M a cube. So this will be the angular frequency, but in option it is written in terms of k, so we can write 1 by 4 pi epsilon naught, that is Coulomb constant. 1 by 4 pi epsilon naught is equals to k. So what we'll get here, we'll get a 6k q square divided by m into a cube. M into a cube. So this will be the angular frequency. Angular frequency in this case. Okay, sorry, in this case these two charges are not equal. The charge that is placed at the vertices, that is q, but this charge is written minus q naught, so it will be q into q naught. Q into q naught, everywhere you can change this. This will be q into q naught, this will also be q into q naught, this will also be q into q naught. So this will also be q into q naught, and this will also be q into q naught. So correct option will be option B. Option B. Okay. Then question number 18, where it is written here, two-dimensional electric field is defined is equals to S. The correct diagram for this line force. This I think you can draw by yourself. I'm leaving for you. What you have to do, you have to just every point you have to just see the magnitude. You have to put, it is written that E is equals to minus xi cap plus yj cap. So first you have to find out the value of this electric field, I mean magnitude as well as direction. Your magnitude will be given by the length of the arrow, and directions will be given by the what will be the direction of this vector. Let's say if you put x equals to 0, y equals to 0, then electric field will be 0. And on the positive x-axis, if you put say x equals to 1, y will be 0, so then it will be minus I cap direction. So on the x-axis it will be minus I cap, and on the minus x-axis it will be plus I cap. And then also you can calculate what will be the electric field on y-axis. So on the y-axis it will be plus y cap, and minus y-axis it will be minus y cap. So I think correct option, which option will be correct? Option A will be correct. You see on the x-axis electric field in minus x direction, and on the minus x-axis it will be plus I direction, and on the positive y-axis it will be plus I cap direction, and on the negative y-axis it will be minus y cap direction. So like this. But you can see here the minus y cap, they have actually replaced this y cap direction upward. There it is downward, it is upward, so this cannot be correct. Here also you can see both the x-axis, positive x-axis is supposed to be minus x cap, but here it is plus x cap, so this cannot be correct. And here also you can see on the y-axis, positive y-axis is supposed to be upward direction, that is positive y direction, but it is shown in the figure downward direction, and negative y direction is supposed to be minus y cap direction, but it is given upward direction, so this cannot be also correct. So only one option is correct, that is option A. Option A will be correct. Good. Okay, then question number 19. In question number 19, it is written a circular disk of radius r carries a uniform surface charge density sigma, is placed in the xy plane and its center at the origin. Consider a point on the axis 0, 0, z. Okay, let me do a figure first. Let's say this is our charge carrying circular disk. And this is placed at the xy plane and center is at the origin. So let's say this is x-axis, this is y-axis, and z-axis is parallel to the axis of this loop. Okay, so this is the z-axis. Then what has been asked, let's consider a point on the z-axis. Okay, consider a point on the z-axis whose coordinate is 0, 0, z. That's mean the distance of this point from the origin, from the loop, perpendicular distance. This distance is z. Now what has been asked here? So option A, that's been asked, the electric field will vary with the distance as E is proportional to 1 by z square when z is much greater than r. Okay. So before solve this question, just since it is related to the electric field, so let me just write electric field on the axis at a distance z from the charge carrying circular disk. Surface charge density sigma. So in this case, we have in last class we have already calculated this electric field. That electric field will be sigma divided by 2 epsilon naught 1 minus z divided by under root of z square plus radius r, so r square. And if it is above the loop, then it will be plus z cap. If it is minus below the loop, then it will be minus z cap. Okay. Okay. So then what has been asked here, I think we have also discussed this limiting case. So when z is much greater than r, that is from the large distance, if we look at this circular disk, this whole disk will be applied as a point. So charge on this disk also be applied as a point. So this electric field which actually vary 1 by z square, that is electric field because of point charge. So option C is correct. When z is much greater than r, then we have already calculated it in the last class that electric field actually will vary like 1. We have like a point charge, so it will follow like 1 by z square. So option C is correct. Then option B, the electric field is discontinuous at z equals to 0. This option is also correct, because last class we have also shown you. At the center, if you consider a point, around this point, because of other charges, electric field will be 0, but at center there will be some charge, and that charge actually create a electric field on the above the loop upward direction, below the loop downward direction, and because of it there will be discontinuity of electric field. So option B is also correct. Option B is also correct. And then first derivative of electric field at z equals to 0 is sigma divided by epsilon naught delta z. Yeah. Okay, for that let me just read all the variations of electric field as we have discussed in last class. So let's say this is z and this is the directions of electric field. I mean electric field and the y-axis. So on positive z direction it will be varies like this, and on negative z-axis it will also vary like this. And then we have written the value of this electric field at this point is sigma by 2 epsilon naught. Here also it will be sigma by 2 epsilon naught minus sigma by 2 epsilon naught. So if any function, you can write one statement here, if any function have a finite amount of discontinuity at any point, and if you take the derivative of this point of this function at this point, that will give you actually a Dirac delta function at this point. So in this case you can see that z equals to 0 point, that is on the surface of this charge carrying this electric field is discontinuous, and amount of discontinuity we have written in last class also, it will be q by epsilon naught. So finite amount of discontinuous. So in this case electric field is a function of z and it has a finite amount of discontinuity at z equals to 0. So therefore if we want to calculate the first derivative of electric field at z equals to 0, that will give you actually the amount of discontinuity at this position. So it we have already calculated in last class, sigma by epsilon naught. This is the amount of discontinuity. How we can calculate amount of discontinuity? The value of this function right side minus the value of this function on the left side at this point. So in this case z equals to 0 point, right side is sigma by 2 epsilon naught, left side is sigma by minus 2 epsilon naught. So when you take a difference of these two electric field, that will give you sigma by epsilon naught. So amount of discontinuity into Dirac delta function. Okay, so option C is also correct. So what is the logic? If a function has a finite amount of discontinuity at any point, the derivative of this function at this point will give you Dirac delta function into the amount of discontinuity. Why it will give you Dirac delta function? Because when you look at this function from left side or right side, both tends to 0. That's mean delta x, delta z will be 0. But for when you go from left side to right side, delta z is 0, but delta e is not 0. So something non-zero divided by 0, what that will give you? That will give you infinite. And we also know that delta z equals to 0, it will be infinite. So that's why it's replaced by delta z, Dirac delta function. Okay, so if any function have a finite amount of discontinuity at any point, then the first derivative of this function at this point will be the amount of discontinuity into Dirac delta function. So in this case, amount of discontinuity to sigma by epsilon naught and Dirac delta function at z equals to 0. So option C is also correct. Option C is also correct. And then what is written here? If r tends to infinity. Yeah. So now if this r tends to infinity, if we put this, if we make this radius of this loop is infinite, that means this charge carrying loop will behave like as a charge carrying infinite plane. So in that case, again, electric field at any point above the loop and below the loop will be magnitude will be sigma by epsilon naught, and above the plate will be sigma by 2 epsilon naught, and below the plate will be sigma by 2 epsilon minus z cap. Above the loop it will be plus z cap, below the loop it will be minus z cap. So option D is also correct. And these are already we have calculated in last class, so you can just take a look on them. Okay. So option A, B, C, D all are correct here. Good. So now this is the last questions for today's class. So what is written here? A wooden block performs SHM on a frictionless surface with frequency nu naught. The block carries a charge plus q on its surface. If now a uniform electric field E, something from here. So electric field is E is switched on as shown in the figure, then the SHM motion of the block will of same frequency, of same mean position, with shifted mean position, or changed frequency. Okay, so what has been asked in this question? So before that, just try to understand the statement. Let's say we have a frictionless table, and the end of this frictionless table is connected with some rigid wall. Now what I'm doing here, I have placed a wooden block on this frictionless surface, and we have connected this frictionless this wooden block with a spring. So one end of the spring is connected to the rigid wall like this, and another end is connected to the wooden block. And let's say the spring have a spring constant K. Spring constant K. So before applying any electric field, if we give a little displacement of this charge, but and before giving any displacement, let's say it's a equilibrium. So spring at this moment has its relaxation length. So there is no compression, there is no extension of the spring. So there will be no force on this wooden block. So this block will remain at rest at this position. So now this is the position of this if we say the length of this the relaxation length of this loop spring is say L naught. So it will be rest at a distance L naught from the rigid wall. Now if I give a little displacement towards right, so let me draw another figure. So initially this block was here. Now what I'm doing here, I'm giving you little bit displacement towards right. So let's say block is here. So if we give a small displacement to the block towards right. So because of that, let's say this displacement is x, so that's mean the spring is compressed by the length x. So now we have this we have compressed this spring because of by displacing this block. So there will be a restoring force on the spring, and it will be proportional to the its length. So kx amount of force, and that force will be applied on the block because by the spring. And what will be the direction of this force? This force will be along this direction, because spring will try to get back its original position, original length. And how it will get original length? So for that, actually you will apply the force on the towards the block towards the right, so that the block can move its original position, and then again spring will get its proper length. Okay, L naught. But after giving this displacement, if we just leave this block here, then what will happen? Spring will apply a force which will be k into x, and because of this force, this block will start moving towards right. Block will start moving towards right. So during this motion, during this this motion, the time it will take during this travel the distance x. During this time, spring will constantly apply some force on the block, and because of that, it will gain some kinetic energy. So after some times, the block will come back its original position here, initial position. But by this time, during the traveling this distance x, it will gain some kinetic energy. And because of this kinetic energy, when block will come at this initial position, it will not be at rest. Now it will travel towards the, it will cross this line, and then it will start traveling toward the right, towards the left. But as soon as it will cross this line and it will travel towards the left, now the spring will get elongation. The length of the spring will increase. So again, if the length of the spring will increase, so spring again it will try to get back its original length. So because of that, the force on the block will be now towards left. So because of this force, this block will oscillate left right about this line, that is at a distance L, this perpendicular line. So this at a distance L, there will be a mean position of the loop where the block will be at rest. But if you give a little displacement of this block, it will oscillate about this, around this block, around this length. The block will oscillate around this line. And what will be the oscillations frequency? For that, simply we can write the force on the block after displacement, the x will be minus k into x, because we are displacing this force. We have displaced this block towards right, but the force that is acting on the block is towards left. So we can write F is equals to minus kx. And then if we replace this force F is equals to mass into acceleration, so we can write m into dx by dt square is equals to minus k into x. So now if you divided this m on the both sides, so what we'll get, d square x by dt square is equals to minus k divided by m into x. So it's a standard differential equation of HM motion. So what we can write, that angular frequency omega is equals to under root of k divided by m, and linear frequency f is equals to 2 pi by omega. So it will give you 2 pi m divided by k. Okay. Sorry. Omega equals to 2 pi into nu, and we can write nu is equals to omega by 2 pi. Omega by 2 pi. Linear frequency nu will be, in this case it is written nu naught in the question, so nu naught equals to omega by 2 pi. Omega by 2 pi. So for the first case, without applying an electric field, this time the frequency of the oscillations will be 1 by 2 pi under root of k divided by m. K divided by M. Now in second case, it is written here that now this block is carrying a charge plus Q, and we'll turn on an electric field, uniform electric field E, towards the right. Towards the right. So again, let me draw a figure first. This is frictionless surface and this is the rigid wall. When we did not apply any electric field, let's say block was at rest at this position at a distance L0 from the rigid wall. At a distance L0 from the rigid wall, first case. And then if we give a displacement without applying an electric field, it will oscillate around this line. That's mean we'll get a point at a distance L0. So around this point it will oscillate. But now, as soon as we'll apply this electric field, what will going to happen? So this electric field, and we are putting some charge on the Q, charge on the block, that is plus Q. So now if we place this charge carrying block in an external electric field, which electric field is actually towards right, so the force on this charge particle because of this electric field will be Q into E. So that force, because of that force, since this block is free to move on the surface, so it will start moving towards the right. Start moving towards the right. But as it will move towards the right, the spring will get compression, and because of that, spring will start also applying some force on the block, but that force will be towards left. So after some point or after some time, we'll see that these two force will be equal. One force because of external electric field that will be acting on towards right, and what will be this force? Q into E. And now because of this force, the spring will get a compression. And let's say if this distance is x0, initial position was here and now block is here. So if this distance is x0, then so the spring will be compressed by this length x0. So because of that, there will be force on the block that will be towards right, and that force will be K into x0. Now these two forces are opposite to each other. Since this Q into E, it will be always constant, so because of that, the block will start moving, and as it will moving towards the right, the spring will get elongation, compression. As it will move towards right, spring will get more compression. So at some point, what we'll notice that these two forces will be equal. These two forces will be equal. So at this position, block will be at rest. Block will be at rest. So at what position block will be at rest? When the Q into E will be equal to the K into x0. So we can find out x0. So x0 will be Q into capital E divided by K. So this certain value of x0, that's mean this new position where before applied electric field, its equilibrium position was at a distance L0. But after applying electric field, this equilibrium position will shift. At this position, the net force on the block will be 0. So now this distance is no more L0. This will be L0 minus x0. So that's mean we can say that the equilibrium position of the block is shift now by the distance QE divided by K, where K is the spring constant. And then if we give a little bit more displacement of this to this block towards right, then what will going to happen? Now I am giving a little bit more displacement to the block towards right, and let's say this distance is very small distance, and let's say this distance is x. This distance is x. So if we compare with the initial position, then what will be the total displacement of these blocks from its initial position, x naught plus x, x naught plus x. So the net force that will be acts on this block because of the spring, that will be k into x naught, k into x naught plus x, and that force will be along towards left direction. That force will be along, that force will acting towards leftward, towards the left, is in this direction. And this q into e, that will be always towards right, and that is always constant. Q into e, that is always constant. So at this moment, if I calculate the net force on the charged particle, net force on the block, what will be that net force? F will be, so we are giving this displacement, this charged particle towards right, but the force that will be acting on the block because of the spring, it will be towards left, so it is opposite to the motion. So we have to write minus k x naught plus x, and we have also, because of this electric field, there will be a force which will be along the motion of the block. We are giving displacement towards right, and this force is also acting towards right. So this force is acting along towards right, so we can write q into e. So that will be the net force on this charged particle at this position, at this position. So now if we say, we write the, in terms of mass into acceleration, this force in terms of mass into acceleration, so we can write m into dx by dt square is equals to, what we'll get, minus k x naught minus kx plus qe, qe. Now according to this new equilibrium position, at this position these two forces must be equal. These two forces must be equal. So what we can write here, these two must be equal and they are opposite to each other, so they will cancel out each other. So at the displacement, that is x naught plus x, at this position, the net force on the particle will be dx by dt square is equals to minus kx, minus kx. So again, this is will be also motion of SHM motion. So in this case also, if we want to calculate the angular frequency, so it will be dx by dt square is equals to minus k by m into x. So angular frequency will be under root of k divided by m. So the linear frequency in this case will be 2 pi, 1 by 2 pi into k divided by m. So both the cases you can see, before applying electric field, the angular frequency was 1 by 2 pi under root k divided by m. Even after applying the electric field also, we are getting the same frequency, 2 pi, 1 by 2 pi under root k by m. But what has been changed because of this external electric field? The equilibrium position. Initially it was oscillating about around the length, or at a point which is at a distance L naught from this rigid wall, but now this block will oscillate around this point, And what is the distance of this point? This distance of this point from the rigid wall is L minus x naught. L minus x naught. So equilibrium position actually in this case will shift. Equilibrium position has been shifted from initial equilibrium position, but both the cases, the angular frequency will remain same, as well as linear frequency will also remain same. Okay, so both the cases frequency will not change, but mean position will shift. First case, the mean position was at a distance L naught from the rigid wall, but in second case, after applying external electric field, the new equilibrium position will be at a distance L naught minus x naught, which is less than the distance of L naught. So in this case, we can say that mean position will shift, but angular frequency or oscillations frequency in both the cases will remain same. So which options will be the correct then? With same mean position, no, this is not correct. With same frequency, this is correct. With shifted mean position, this is correct. And change of frequency, not correct. Frequency will remain same. So in this case, two options will be correct, option A and option C. Option A and option C are correct. These two options are correct. Equilibrium position will shift, but the angular frequency or oscillations frequency will remain same. Okay, so I hope you got some idea how to calculate different type of questions using the concept that already we have discussed in class. So today is the Sunday, so at the evening I will upload one test paper. Maybe this time the number of questions will be 10 and you will get 30 minutes to solve it. So let's see how many questions you can solve correctly. Okay, so thank you for watching this video and we'll see you in the next video.